Yes, we've started with okay, excellent. So we're up and running. Thanks for your patience and sorry about the delays. It's a great pleasure to welcome David Berenstein, who needs very little introduction to this audience, but he's visiting us this week until Saturday, I believe.
Well, yeah, well, I live Saturday.
Until
Takes a while to get to the
airport. Excluding Saturday. But he is visiting us from UC Santa Barbara via University of Amsterdam.
Yes.
So he's going to tell us about staggered bosons.
Yes. So thank you. So this is based on two papers, one from March of last year and the other one from November. In the first paper, I introduced the name staggered bosons. That was suggested to me by lattice people. I'll explain where that comes from. And in the second paper, I understood what I was doing in the first paper. That's one way to put it. So there were some interesting observations on the first paper that ended up being related to a lot of recent developments on non-invertible symmetries that I didn't know anything about on March, and it took a while to figure that out. And once that was figured out, it worked a lot better. Okay, so and this is based, on two papers, and the second paper was with my graduate students, Thomas. Great. So what I've been thinking about lately, because one of the issues is that we getting money to think about how to put field theories on quantum computers, which means you have to think in Hamiltonian language. So quantum computers take quantum states and evolve them via some effective Hamiltonian evolution. So a lot of the field theory that I grew up with when I was in graduate school was the Lagrangians, and then I had to think about Hamiltonian physics lately. And then the goal is to find interesting field theories with a finite number of states per unit volume that can eventually be seen. That's kind of the idea of how you do field theory with a quantum computer. And the big question is there anything in Hamiltonian physics that's sufficiently distinct from Lagrangian, where you can get something new which would not be available in a naive path interpret? So we simulate Hamiltonians and Lagrangians, and basically, when you have both momenta and position, that's how we think of quantum mechanics, and real time, there's usually not a guarantee that there will be a weak rotation to Euclidean field theory, which is what pattern the boson usually. So there can be some intrinsically Hamiltonian physics that should be analyzed without integrating out the piece, so to speak, so that there's something going on. And what I'm going to tell you about is exactly about this idea about how to think on Hamiltonian physics in a slightly different way than usual. So, as I said, I'm going to look for interesting lattice realizations of field theories that are gapless. Those are the ones that eventually have a chance of being relativistic in the low energy physics. I want to claim that they enjoy some symmetry protection that's not available in conventional field theories. It turns out that this non-conventional stuff ended up being related to non-invertible symmetries, although the first argument doesn't seem to be related to non-invertible symmetries. And then I'm basically going to talk about the idea of a half boson in one dimension and generalizations. And I have to tell you in what sense a half boson is a half boson rather than a full boson. So the outline that I'm going to follow is, first I'm going to tell you about a quantum field theory of the canonical boson as a model of something that has half as many degrees of freedom than a regular boson. So a canonical boson has only left movers, whereas a regular boson has left movers and right movers. So in that sense, you have half as many movers. Then I'll tell you how to turn that into an idea for how to get half bosons on a lattice. It's not going to be the Carrel boson, because the Carrel boson is anomalous and you cannot put it on a lattice. And then we'll talk a lot about, the model's topology, also known as the problem of zero nodes in this case. And then I'll describe a little bit the difference between automorphisms of the algebra that generate the model versus symmetries, meaning automorphisms that are realized in the Hilbert space itself. And that's the clue to understand non-invertible symmetries, that symmetry on an algebra might not be realized on the representation here. So one has to work with this idea. And this is what non-invertible symmetries are going to be, is basically that they don't quite get realized fully. The algebra automorphisms act fully only on a subset of the Hilbert space. In some places you have to get rid of things. And then I'll tell you how to build half bosons from regular bosons. And then I'll go to some other models that are based on these, which are something called clock model spin chains, which are related also to parafermions and other constructions. I'm not going to describe the parafermion construction, but they're known from parafermions. And then they do have a Kramers-Van duality, and in this case, one can check that the Kramers-Van duality of the clock model is the same thing as the T-duality that I was talking about in the half boson. And then that lets us use these ideas to do something about identifying critical points. And then I'll talk a little bit about generalizations to higher dimensions, where one ends up with fractal dynamics. Okay, so let's start with the idea of what is a half boson. So the typical example is the left-moving boson. There's only a left mover. The equation motion, rather than being second order, is first order. That's one way to think about halving the number of degrees of freedom. There's a certain sense in which people don't like this theory, in string theory, because it's anomalous, right? The left Carrel boson has an anomaly, and when you try to write the partition function, it's not modular invariant, and then if you like modular invariance, then this is not the theory you start. Nevertheless, so that's a statement about the Hamiltonian version versus the Euclidean version. The Euclidean version, that's where you would compute the partition function, and where one would expect that it's modular invariant. Nevertheless, if you look at this theory, it is actually a Lorentz covariant relativistic field theory. There is a Hamiltonian formulation where you write a Hamiltonian written in terms of the variable phi, and what one does is one introduces the Poisson brackets of phi. And let me be very precise. This is a way to define a Poisson bracket with the field at x and the field at a different position x prime. And because the equations of motion are first order as opposed to second order, to get a first order equation, one cannot have the phi dot floating around in the Hamiltonian. So the Poisson bracket is built by saying it's local, so there's a delta function x minus x prime, but it needs to be antisymmetric. So since the delta function is symmetric, when you take a derivative, it becomes antisymmetric. And once you have an antisymmetric tensor, you have a proper Poisson bracket. This is a C number on the right-hand side. You can just compute the equation of motion by taking Poisson brackets with Hamilton. If you don't like Poisson brackets and you prefer to have commutators, just add a factor of I and set each bar equal to 1, and none of the equations will really change. The important point is that you take the Hamiltonian, and then the simplest Hamiltonian that you write is the integral of phi squared over 2 times a constant. That's 2 fixed units, and that constant c is basically the speed of light. And then if you look at this Hamiltonian, because it's just phi squared, there's nothing of lower order in phi that one can add that would add a mass to it. And if you add phi, you can actually remove it by shift. So the idea is that if you look at this Hamiltonian in these variables, there's no relevant information. And then the usual proof that you cannot get rid of the gap is that the theory has a non-trivial anomaly in the V. It's a U1, it's a Staggered Bosons, so it has a non-trivial U1 or a non-trivial C left central charge different than C right. And anomaly matching tells you that that needs to survive in infrared, so you can't get rid of it. So what are these commutation relations I showed you? So if you say boson brackets are commutators in quantum theory, this is what's known as the C=1 current algebra in position space. So if instead of using the commutator of the Fourier modes of J, you use the J's at position, the commutators of J being the derivative of the delta function, that's the Schwinger term. In complex analysis, a derivative of delta function is 1 over z minus z prime squared when you do contour integrals. So that's basically the current algebra relation. I just didn't call phi j at the beginning, so I was trying to mislead you. Okay, but the idea is that the right-hand side, which is this derivative of the delta function, is what people usually call the anomaly of the current algebra. It's the energy of the first excited state on top of the vacuum. So if the theory is gapless at infinite volume, what that means is that there's long wavelength excitations that cost essentially zero energy. Okay. That's condensed matter speak as opposed to particle physics speak. Okay. So now I want to turn this problem into a lattice question. So I want to work the idea of having something that's like a half boson on a lattice. I just told you a continuum version of the half boson is a Staggered boson, but now I want to go to a lattice. But the idea is that if you're on a lattice, you go to the deep UV, meaning distances that are shorter than the lattice scale, there's nothing. So there's no anomaly there, the C left and the C right are the same. So if a theory produces a left mover, then only a left mover, then you would violate the anomaly matching from the UV to the infrared. So you also will get a right mover. So the question is, what do you get? And this is the question of, do you get a massless theory, or do you get something that's not massless, meaning gapped? So if you get a massless theory or gapless, we call it success. And if we get a gapped theory, then it's a trivial vacuum in the deep infrared. So now I want to tell you how to make a half boson. So what's the idea? You have a lattice, you have bosonic variables, and instead of having a position and a momentum at each lattice side, we're going to halve the variables. So we go to one commuting variable, so to speak, or one bosonic-like variable per lattice side. And the idea is to make something interesting out of it. So we want to still have a non-trivial boson bracket, but the bracket of a variable with itself is always zero. It's a statement about boson brackets. So the only way to get something non-trivial is to shift the boson bracket to the neighbors. So to have the variable at lattice side I talk to the neighbor at lattice side I plus 1 and I minus 1. That's the simplest way to get a non-trivial boson bracket. So the idea is to basically take the boson brackets of Q's and basically say, make a constant matrix, which is plus 1 to the right, minus 1 to the left, and that is an anti-symmetric matrix. So I have to choose a sign, the plus 1 to the right versus minus 1 to the left. That sign choice, it could have been minus 1 to the right and plus 1 to the left. So I'm going to call this sign choice left moving. There's a change of variables that changes the left moving sign to the right moving sign, but I need to make a choice. So once I make this choice, I get some Q variables. What I put is something that has a discrete version of a delta function between two neighbors and a discrete delta function on the other two neighbors. I put a minus sign. So this is a discretized version of the derivative of the delta function. This is actually how this started. I was trying to understand some problems, some conjectures I had that I needed to verify some more general versions of this Staggered boson, and I was trying to compute them because I couldn't compute them directly. So I wanted to kind of simulate them. So this is what showed up. So when you have this Poisson bracket matrix, it's constant and anti-symmetric, and therefore defines a fixed space. Okay, this is in the sense of having some Poisson bracket manifold that has a Jacobi identity that's consistent. Okay, so I'm just going to take my Poisson bracket, take the simplest Hamiltonian I can imagine, which is just taking the Hamiltonian of the continuum theory and just writing it in these discrete variables and see what one gets. So I just write a Hamiltonian, which is 1/2 sum of q squared, that replaces the integral of I squared. And if I compute the equations of motion, I find that qi dot ends up talking to two nearest neighbors with a minus sign. So if I'm very naive about it, what I find is that q dot is the derivative of q with respect to x. So this model naively discretizes the Staggered boson. So let's analyze the full model. The idea is that the system is quadratic and it's free in some sense. It's a bunch of harmonic oscillators and there's translation variance. You can just do more expansion by doing Fourier analysis in position space. And then because the equation of motion is first order, omega of k doesn't have a square root that we will get from a second order derivative in time. Instead, what we have is that omega of k is a single value function of k, which is -2 sin k. If you're familiar with the doubling problem for fermions, the fact that there's two zeros over here in omega at k equal to 0 and omega at k equal to pi, the fact that there's two crossings, this is what people would call the doubler. So this is the statement that the doubler of the left moving boson is the right mover. And then the system has to have a right mover, which means that there's some other place where omega vanishes. So when you look at how people talk about staggered fermions, this is one way to ameliorate the doubling problem in field theories, but the idea is the same. You get a doubler, so you get two modes. One of them is the left moving fermion, and the other one is the right moving fermion in two dimensions. So it's straightforward to quantize. Whether something is a raising or lowering operator will depend on the sign of omega k. Omega of minus k is minus omega of k. And that's the statement that the mode at omega k is conjugation of 1 minus k. So the idea is that instead of having one raising and one lowering operator at momentum k and minus k each, you only have one raising operator at momentum k and the lowering operator is at momentum minus k, and you don't have a second raising operator in the second order. And this is the sense in which you've gotten away with having half as many degrees of freedom as usual. Okay, so the infrared is omega of k equals 0. The left movers are going to be things where the wavelength is very, very slow. So k is approximately equal to 0. The nearby values of phi are ferromagnetically ordered in the sense of they're all pointing roughly in the same direction. And then for the right movers, it's at k equal to pi, so there's a maximum sign change at omega small between the neighbor and the nearest neighbor. And that's what one calls antiferromagnetic or mean ordered in metaphysics. And the statement is that some modes are at k equal to 0, the other ones are at k equal to pi. Now, the important thing here is that omega of k is a single function of k. So even if I deform my Hamiltonian, even if I make it more complicated, even if I try to move around the dispersion relation, this is controlled by the fact that if I have a function from a circle, which is the Brillouin zone, to the real numbers, and it is continuous. If there's one crossing of 0, there needs to be another crossing of 0. And you cannot get rid of the fact that omega of k is conjugate or that k is conjugate to minus k. So the two crossings of 0 will always be at 0 perhaps, or pi, sorry. So the idea is that you cannot get rid of these crossings of 0, so that's what kind of keeps the theory gapless. And it's important that when I make this claim, what I'm stating is a statement about if I keep translation variance, then the mode at k equal to pi and the mode at k equal to 0, they're in different locations in the weaving zone. So if I keep translation invariance, I cannot switch momentum 0 and suddenly hybridize or mix with the one at momentum k equal to pi. So the idea is that this kind of prevents the system from developing a gap. So if I change variables to the mean ordering, mean go to the where every at every step I make a sign change. Then I turn the left moving Poisson bracket into a right moving Poisson bracket. And it changes just basically changes what the k equal to 0 and k equal to pi correspond to. Basically the symmetry protection is basically that the left mover and the right mover cannot be put at the same value of k. Atlas bosons are protected even when you add perturbative interactions which preserve translation values. It's a critical theory now in the sense that since omega goes to 0 and k equal to 0 and pi, you can actually put it on a finite volume and you can go to low frequency calculation. And then there's essentially only one positive frequency per node n, that's going to be the left mover. So you can count degrees of freedom and you get the same number of degrees of freedom as a C-1 boson. And then if you go to the infinite line, you can try to understand what happens at zero momentum. And what you find is that there's two central elements in the algebra. One is the sum over the Q over all the even ones that commutes with everything. That's central in the sense that the Poisson bracket of the is even with any other variable is 0. Basically, anytime you take a Q to the two a Q, you get a +1 from one neighbor and -1 from the other one, so things will cancel. And you can do the same with the other one. So the idea is that the true algebra that we have in the infinite volume has two zero nodes. There's these two central elements. So it's not quite a Poisson bracket in the sense that it's not degenerate, it's a degenerate Poisson bracket. So when you quantize, you have to be very careful with what these numbers actually mean. If you do things on a finite volume, and you have an even number of sides, you can have either an even, well, you always have an even number of zero modes, but it can be either two zero modes or zero zero modes, depending on whether you put periodic or anti-periodic boundary conditions for it. And when you have an odd lattice sides, or a lattice with an odd number of sides, you get one zero mode, regardless of this periodic versus anti-periodic. So, how does it work? When you have an even number of sides and periodic boundary conditions, there's a clear distinction between what an odd side and an even side is. So therefore, the two zero modes, the C even and the C odd, survive. But if you have anti-periodic boundary conditions, then the constant solution will change sign as you cross 0, so there's no constant solution, so the modes get kind of moved away from the at zero frequency. The solution at zero frequency with anti-periodic boundary conditions is zero. So the idea is that you look at the two possible solutions, periodic and anti-periodic. Either you get two zero modes when you have periodic boundary conditions, or you get 0 when you use anti-periodic boundary conditions. And when you look at parity, and parity in this case is the one that turns the left mover into right mover, and that basically uses the neat ordering and reverses the size of the lattice. In this graph, that's basically done by reflecting the figure along the vertical axis. So if you put the left mover on the left, 0 mode on the left, and the right moving 0 mode on the right, and you do this reflection, the two zero modes will swap. When you go from when you act with parity. Okay. When you have an odd number of lattice sides, there's one zero mode. Basically, when you put them on the circle, you find that since you have an odd number of variables, the Poisson bracket being an antisymmetric matrix, the number of zero eigenvalues of that is always odd, so it's at least one, and there's only one. And then if you have a zero mode for the left movers, the right moving zero mode is absent. And what happened is that the left moving zero mode ends up being quantized with periodic boundary conditions. That's what produces the zero mode, or the zero mode. And the right moving mode gets kind of quantized with anti-periodic boundary conditions. Okay, so the reason you always get an odd number of zero modes in this case is that a non-degenerate Poisson bracket always requires an even number of variables, and therefore there's always one variable that commutes with everything. It's a statement about this. So the number of zero modes depends on whether the number of lattice sites is even or odd. One would think that in the continuum that doesn't matter, but it actually does, right? So the statement is that even if you go to the thermodynamic limit where the circle is big, there's still a difference between having an odd number of lattice sites and even number of lattice sites. So there's something weird going on.
So in the continuum limit, you get back the chiral boson.
So you get both bosons, you get the left moving and the right.
Yeah, so you're doubling the original problem.
Yes.
Because originally, so really it doesn't matter, we think that the chiral boson exists on the boundary of an higher dimensional system.
Yeah, but this is not.
It's a completely different. Yeah.
This is not that story.
Right. So you play always with left and right at the end.
Yes. In the end, you always play with the left and right, but there's an issue of whether you have periodic versus anti-periodic boundary conditions.
Okay, but you have both. Okay.
Yeah. Okay. You do things on an open interval, the same thing happens. If you have an odd number of sites, you always get one zero mode no matter what you do, because you have an odd number of variables in your Poisson bracket. And this is similar to what happens when you have Neumann-Neumann boundary conditions. If you have an even number of sites, there's no zero mode in this case. And then there's the Neumann boundary conditions, because when you work on an open interval, you've cut the Poisson brackets at the end, so you do actually get a non-degenerate Poisson bracket structure. If you know about Kitaev's Majorana zero modes, this sounds very similar. The number of Majorana zero modes depends on whether there's an even or an odd number of lattice sites. Yeah. And then you can ask, why does this look so similar? The reason is that when you pair Majorana modes to get a frequency or to make a mass matrix, the mass matrix of the Majorana fermions is also an antisymmetric matrix. So when you try to pair and cap the system, you have to do it in pairs. And then, because it's an antisymmetric matrix, there's always a zero mode out if you have an odd number of lattice sites. And it's the same argument over here. They both depend on whether a matrix is symmetric or antisymmetric.
But usually in the Majorana context, let's say the Kitaev chain are gapless, right? You're playing the gapless chain, right?
Yes.
So yeah.
Again, this is a statement about zero modes. This is topology. This is not.
Yeah, so they are not localized. I mean, they are not localized.
Right. Yeah. Absolutely. Okay. So now let's go back to the question of translational symmetry. All my arguments were kind of mathematical physics. There's the question of what is translational symmetry in the lattice. So is Qj going to Qj plus 1 on a periodic system? Is it a symmetry? And the problem is the zero modes. So if you look at the zero modes more carefully, when you change Qi to Qj plus 1, it changes an even side to an odd side. So what this does is that it swaps the C odd and the C even when you make the translation method. Now, because C odd and C even are central, in any representation of in any reducible representation of the algebra, the C odd and the C even will be C numbers, and they will be usually distinct. And when you apply this kind of Qj to Qj plus 1 symmetry, you have to ask, am I allowed to swap the two zero mode expectation values in the representation theory of the algebra? So as an algebraic statement, the Qj to Qj plus 1, obviously I didn't change the Poisson brackets or the commutators. So this is definitely a symmetry of the algebra in the sense that all the algebra relations are the same before and after. So we call that automorphism of the algebra. And because of this property of the zero modes, that it changes one central element for another one, you cannot do that within the algebra itself because there's no operation that allows you to do that. There's nothing that has that allows you to make that change. So that's why we call it an outer automorphism of the algebra. So when you have the non-zero modes, meaning the oscillators, the Stone-von Neumann theorem is the one that tells you that if you have the XP commutators and they're equal to 1, then you have a harmonic oscillator type Newtonian. There's a unique irreducible representation. And when you change the algebra to something that has the same algebra, you can always lift it up to a unitary acting on the states. So basically, all the non-zero modes go along for the ride, and there's you can lift whatever action you have to the non-zero modes automatically. It's only the zero modes that give you any obstruction. This is the hallmark of topology, that only the zero modes matter for this question. So whether something is a symmetry or not in this case depends on the Hilbert space. What are the allowed values of C odds even, which show up in physics? So there's observables, there's representations. Representation theory is the statement of what is my Hilbert space as opposed to what is my algebra of operators. So the question now is about the Hilbert space of the zero modes. What are the allowed values? Zero modes. And then at the level of zero modes, we have no guarantee that it is a symmetry of all the representations put together. So you have a list of pairs of values that are allowed. And now if you act twice with this morphism of translation by 1, you change the C odd back to the C odd and the C even back to the C even. So there's always something where you're guaranteed to land on the correct same values that you had before. So translation by 2 can always be turned via the Stone-von Neumann theorem into an actual unitary working in the whole full Hilbert space. So translation by 1 and translation by 2 are two completely different objects in this setup. Okay? So this operation of acting twice is like translation by conventional theory. And then it's only kind of a symmetry, translation by 1, on the subsector representations where the labels of the odd and the even ones can be matched. So there's a subspace of the Hilbert space where translation by 1 might be defined, but whether it's the whole Hilbert space or not depends on the labels of these symmetries. So in practice, what is one supposed to do? You make it work on as many states as possible. So you basically pick the labels that have matched pairs, and on all those labels, you generate the biggest symmetry that you can. On the states where you cannot find the corresponding labels, you define translation by 1, trivially meaning you extend by 0. So there's a subset where you can define it, and where you can't, you just call the result 0. So you just have a projector of the Hilbert space that identifies whether a pair of labels is matched or not, and on the pairs that are matched, that's good, they survive the projection. On the pairs where they're not matched, you just say 0, and then this is an operator on the Hilbert space, this projector that commutes with the Hamiltonian. And then when you apply this translation by 1 twice, I'm going to call this translation by 1D. It's going to be called the duality operator. So D squared is going to be translation by 2, which we saw was a symmetry, so I'm really going to call that translation. And then the projector needs to come in because I kill the states that don't satisfy the condition when I activate. And then the fact that you get something that's like a unitary in translation times a projector, the projector is what makes it into non-invertible symmetries because there's no notion of pi inverse. So this is not a symmetry in the sense that it's a unitary operator acting on the Hilbert space, taking one state to another one. There's some states that are killed by it. Okay. Now I need to tell you how to build half bosons from regular bosons, because otherwise this is all very abstract. So I need to tell you what this translation by 1 really is in a system where we understand that this is better. So what's the idea? There's 2 ways to build projections from bosons. The first one is you take the regular XP variables and you just pick half of the variables for the Q variable, So you take a P at one side and an X at the next side, and you can check that the Poisson brackets of the Q's that are built this way are the ones that I told you. If you actually consider the ones where you swap X and P, meaning that instead of X, Pi plus Xi plus 1, use Xi plus Pi plus 1. In this case, the W's commute with the Q's, and then if the Q's had left-moving Poisson brackets, the W's have right-moving Poisson brackets. So what happens is that if you start with a full boson, then you can build two half bosons, one which will have the left-moving Poisson bracket and the other one the right-moving Poisson bracket. But when you sum the Q's and you sum the W's, you get the same number, right? You get the sum of all the X's and all the P's. So they share the zero modes. So the idea is that you started with two n variables. You get n variables of the Q's, n variables of the W's. But some of the Q variables and some of the W variables are shared, and it's exactly the zero modes that are shared. And this is how you can start with a non-degenerate Poisson bracket of the X's and P's, and end up with degenerate Poisson brackets of the Q's and W's. It's because some of the variables share the modes. And what's happened is that in the passage from the full bosons to half bosons, you're throwing away the canonical conjugates of the zero modes. Okay? So this is what happened in how one passes to B7. Okay. There's another way to do a projection, which is you say, well, if I have n x's and p's, that's the same thing as having two n q's. So is there a way to pass from the x's and p's on a lattice with n sides to a lattice of two n sides? This is the one that will make it more clearly staggered in the sense of how we think about it. And then what you do is you say on the even side you put the p, and on the odd side you put the differences of the x's. And you can check again that the q even and the q odd have the Poisson brackets that I told you before. And then there's two n variables, but you see that this is a difference of the x's. So when I take it periodically on a circle, one of the zero modes is missing, meaning the, let's say, q odd or the q even. In this case, the q odd. So the idea is that when you start with n, you end up with two n variables, but you're missing one of the zero modes. So when you start with these ideas in the classical setup, you might find that if you start with a regular boson, yes, you get the same algebra, but you're missing one of the zero modes. And then you can ask, well, what if I just put it in by hand? What does that look like? So having a zero mode is having a constant solution of your equations of motion. And then you can say, what happens if I make the q odd to a constant? So you would say xi plus 1 minus xi is a constant. And then when you go around, you will find that as you go around, the last one and the first one have a displacement, and this is what we usually call winding. So the idea is that one of the zero modes is the sum of pi's, which is the center of mass motion of the x's, and the other zero mode is the zero mode for the q2i, which is winding that has been introduced classically in the algebra.
So the zero modes are related to topology. So
Yes,
modifying the topology.
Yes.
Okay.
Yes. So one is center mass momentum. The other one is the winding. And at this level, because I did Poisson brackets and I didn't impose any particular quantization, you just have two classical variables describing momentum and winding. And then what is translation by one? It sends p to the difference of the x's, and the difference of the x's to the next p. So it exchanges the notion of what we call winding and the notion of what we call momentum. And you go to a continuum theory and you change winding and momentum. This is what we call T-duality in a C-equal one function. So the idea is that this system, built this way, secretly is doing something about T-duality as a symmetry. Okay, so what is T-duality? When I was taught T-duality, I was taught it is not a symmetry. It is an equivalence of two theories of different radii that are related to each other, but it's not supposed to be a symmetry. Doing the same translation by twice is doing two T-dualities and it'll add you back in the same theory. It preserves the central elements. And this is the translation by one in the XP variables. So the idea is that translation by two is really translation by one in ordinary lattice. Translation by one is T-duality, and T-duality is not a symmetry. So how do you make T-duality into a symmetry? You first assume something about the C labels. So I'm cheap, so I'm going to assume that they're like in the free boson. Basically, given a set of labels, C left, C right, or C even, C odd, there's a unique irreducible representation. I apply the transformation only on the maximal set of pairs of labels that are mirrored. I assume that the C labels are lattice. And then, how do I make sure that the left movers and the right movers can be mapped? So the left movers and the right movers are mapped in some sense. That tells you that the T-dual and the original theory have some relation between the radii, so some quantizations can pass easily to those. Okay? So they have to have a non-trivial match between some of the winding and some of the momentum, which completes their switches. And as I said, you extend by zero everywhere else, and this is the origin. So the symmetry algebra is again d squared. There's this kind of T-duality kind of transformation, which we want to upgrade to some sort of symmetry. You get translation by two, and you get the projector to match labels. And then I have to tell you something more, which is where does modular invariance come from? So if I want to use T-duality, we usually talk about T-duality when we have modular invariance. From what I've shown you, you just have to put it in my hand. Okay. So we can restrict ourselves to consider lattices of charges that are compatible with the free scalar, or we can restrict it in some other way, but if you want to restrict to the things that in the continuum limit will give you the right partition function for that is modular invariant, that specifies for you the allowed set of values of the C's that you can have. Okay. So let's go back to gaplessness. The argument I gave you about gaplessness was something about this breathing zone, but that was on the translation by one symmetry, but the true translation is translation by two. So what that means is that the breathing zone was doubled in some sense, and it's this doubling of the breathing zone that let me distinguish the 0 versus k equal to pi, which would go both to momentum equal to 0 in the regular lattice translation. So the fact that 0 and pi behave differently is the fact that T-duality works different for left movers and right movers. There's a minus one. The minus one difference is basically the statement about how T-duality works. So T-duality ends up being embedded in the fact that these two things are at different points in k-space. So now the problem is I explained to you that the reason why things were working is because in some sense I was imposing this T-duality and these various other relations secretly in the system. And the duality of translation by one, which is this non-invertible symmetry, is actually doing all the work of saying that k equal to 0, k equal to pi are different. So what I discovered, which was a nice topological argument that seemed completely unrelated to the things, ended up being non-invertible symmetries in this case. Now the idea is I want to go back to the original problem, which is by computers. How do I make models that have a finite number of degrees of freedom per unit lattice site in the sense of a finite Hilbert space? Okay. So if I start with my little Q bosons, translations in the Q space, right? Those are also symmetries of the boson bracket. So what I can do is I can gauge finite translations of the target space, meaning the Q variables. So I can say that instead of using the little Q variables, I'm going to use variables that are invariant on the translation, and I'm going to write a new operator algebra where I just exponentiate the Q's with some number, and I'm going to study the algebra generated by the Ki and their inverses. And then when you compute the commutation relations of the Ki's, instead of having a C number Poisson bracket on the right hand side, if you do it with commutators, stuff behaves nicely. You get to use the Baker-Campbell-Hausdorff formula, and you get some commutator of the Q's, and that produces some non-trivial things. And that's because exponentials of q's are translation operators in the quantum theory. So when you do case translation in X and translation in P, you get magnetic translations and you get phases from these things. So the phase that you get is basically a phase associated with magnetic translations.
So you have a projective representation.
Yes, so now I need to, I haven't gotten rid of the infinite dimensionality. So how do I get rid of the infinite dimensionality? Well, if omega is a root of unity, things work better. Why? Because then k to the n commutes with everything and can be called a C number, and therefore you get rid of the infinite tower of k's, and you get a finite matrix. So if ki to the n is central, we just call it a C number, and then we've gone from an infinite algebra to a finite dimensional algebra. So the algebra itself becomes finite dimensional because polynomials of k get truncated at n, so the polynomial becomes finite. As I said, the reason to do this was quantum computing, and in principle you can put it on a system with finite dimensions. So I produced this system. So this map that I had from half bosons, from bosons to half bosons, can be also passed through this exponentiation. So the Q even was the pi, so the exponential of Q even becomes exponential to the alpha pi, and the k to I plus 1 becomes exponential to the alpha xi plus 1 minus 1, right? And then you say, but now I can use the fact that I have translations in P, and I can also impose them on the X independent to each other. And then have roots of unity. You can check that the k2i and the exponential to the alpha xi become these clock shift matrices. So the k2i becomes, let's say, the Q clock matrix. And then because this shows as xi plus 1 minus xi, you get pi equals inverse. Yeah, plus 1 inverse. And then you can write the simplest Hamiltonian that can be written in terms of these variables. And then basically you sum all the ki's if you want to put some sign and make sure that it's Hermitian, so you have to use ki plus ki. Okay, so the px variables became periodic. We can read the periodicity from how k was made single valued, so that determines the periodicity of the xp variables in the original theory. And then this produces a quantization condition for 0 modes at the level of field theory. And in conformal field theory units, and I'm going to spare you the calculation, we got that the radius was square root of 2 times n, where n is the n by n matrices that you get for the theory. So this was a calculation that we did that we could do now. In the level of the spin chain Hamiltonians, as I said, you just take the simplest Hermitian operator that one can build from these k matrices and just make it translation invariant. And then what you get here is something that involves the Q plus Q inverse, and then this P plus P inverse kind of elements. And these are called clock models. And then this is at criticality at the central point. And what's interesting is that this P cross P inverse is a little bit like a hopping term, and this is a little bit like a transverse matrix. And that becomes clear when you do the simplest example that does this, which is use 2 by 2 matrices, and then the P matrices become poly matrices, and you can make them sigma z, and the Q becomes the poly X matrix, and that gives you the criticalizing in a transverse magnetic field. So the simplest case is omega equals -1, the first non-trivial root of unity. You get criticalizing in a transverse magnetic field, central charge of 1/2. The next one, you get the 3-state pulse models at criticality, which is known to be soluble at criticality via fermions. And then you get spin chains at criticality with central charge equal to 1 when n is greater than or equal to 3. And basically, what was the reason that things behaved? The translation by 1 persisted, so that was still a symmetry. We did the same on all the lattice sides. And this was our non-invertible T duality symmetry. So when we kind of pass down to this lattice model, we preserve this non-trivial symmetry. The symmetry in the new variables is a well-known symmetry. It's called the Hamilton duality. So this one where you take sigma x to sigma z cross sigma z and sigma z cross sigma z to sigma x. So the next one, that's the spin chain realization of Hamiltonians, which is the quantum version of the statistical mechanics solution of the Ising. It's also a non-invertible symmetry, and the spin chain landed at the self-dual. In a bit more detail, because I passed from the full theory to something where I got rid of a lot of variables onto a finite inverse space, you can check that that you take the equivalent of the zero mode becomes this Q charge, and Q to the n is equal to 1. So the structure of the zero modes becomes a Zn charge symmetry. And then there's no corresponding symmetry for P cross P inverse, because when you multiply them around the circle, the P's cancel each other out. So at the level of the representation theory, you see that the left moving or the even zero modes and the odd zero modes are behaving slightly different. And this is where all of these problems about modular invariance will show up. So if you do the statistical partition function of these PQ systems and criticality, they're known to give rise to conformally invariant partition functions in the theory, except that it's very hard to understand the details.
Can we say that you have a parafermionic chain?
Yes, all of these are parafermionic.
Yeah, because it looks like parafermionic chain.
They are parafermionic, you just have to go to these non-trivial
Yeah.
parafermionic variables. And yes, these are all parafermionic. This is
Okay.
okay. So when you have C equal 1, and if you have a U1 current algebra, and with modular invariance, so then you can say something. Then you can say that D squared is translation by 1 in the lattice, the double lattice, times the projection to something, and the projection to something will be that something that was charged. Since there's no image of the charge that's reasonable with the PP inverse, all of that is still projected out. So you have to project to the trivial sector of the Zn charge. So this is what we're going to have as our relation. D squared is equal to D times projection to T equal 1, and this is a projection to the Zn trivial state. Okay? In the infrared long wavelength limit, now you can take T go to 1. Because translation by 2 was a proper translation, and that one, translation by 2 is a UV thing, now in the infrared, that doesn't matter. So you get that D squared is equal to the projection. This is some of the usual way in which this is written in condensed matter systems and in the continuum theories. Okay. The projection to invariance states is a Zn projection, and that's very similar to how one does an orbifold. So the T-dual theory should be identical to the orbifold by Zn. So that's how you can say, if my theory has radius r, the quotient thing takes radius r to radius r over n, that's how you impose the orbifold condition, and then that should be equal to its T-dual. So basically, you can either orbifold or T-dual, and then you get a relation between the two of them, and that tells you that r over n is 2 over r, and then you go back and you find that r is equal to square root of n, which was the computation that I got from these other bosonic variables for free. So just based on the symmetry and the existence of a U1 current algebra, you can determine the CFT radius, and it basically comes out the same as the computations you did. Okay, so people have studied this numerically for various n. So there was a huge number of stuff that people did with DMRG, right? And they found the square root of 2n, and they didn't really give a good explanation for why it was there. It was an observation based on an incredible amount of numerics. Our numerics was on a lattice of size 7 or 8. And trying to identify Virasoro primaries and using some of these techniques. And we were able to determine the radius with a very crude lattice of size 7 or 8. And that was also where we got the square root of 2n numerically. And we found essentially the same. This is how it started. So we first found it on a small lattice, and then we tried to explain it. And the explanation ended up being this thing of T-duality. So, you can ask more stuff. If you now know the radius of the theory at one point in the coupling constant, you can ask what happens when I deform the couplings a little bit. And then you can ask what operators are available that are Z invariant because our theory was Z invariant. So if you start with the theory, dx and d bar x, those are invariant on the Zn. Exponential to the ikx is invariant, so long as k is n times larger than the minimum momentum. Winding states, one is allowed in the setup. And then if you start looking at what's the dimension of these operators where k is, n times the smallest value, for these theories, as a self-developed point that I told you, the HH bar is n over 4 for these operators. So the operator exponential to the ikx is irrelevant if n is bigger than 4. So what that means is that even though you have these operators in the UE, in the infrared, it flows to the conformal field theory of the right central charge and so now we can answer why there was this weird change in behavior for n less than or equal to 4. Basically, when n is equal to 2 or 3, these deformations of the theory that are allowed by Z symmetry are usually generated. And then the relevant operators are part of the effective Hamiltonian, and the theory flows to C less than 1. When n is equal to 4, these things are marginal, and you end up being moved to a different point where the U1 current is subset. So the statement is that the U1 current is there for n bigger than 5. And the other statement is that if you know the symmetry, and you try to deform the theory will be deformed by the marginal operator until the n quarters and quarters gets modified also and until it becomes relevant. So what you'll have is a one-parameter family of conformal theories at a different radius that ends in some Costelli-Stiles transition where winding or momentum or something comes in and the theory moves out. So people know about this. There's a lot of models in condensed matter physics that do this. XXZ is one of those where it's kind of from 0 to 1 in the Z is critical and then it becomes gapped. Okay. Very good. So I told you this thing. If you actually look at the literature, sometimes what you find is that they use that d squared is equal to n times the factor equal to 1. This is a normalization where instead of having 1 here, you have n. The reason why people choose these normalizations comes from math and from some modular invariance of characters and some things to make it a little bit clearer. When the extra factor of n is floating around here, you just rescale the d's in some sense. But that rescaling with this factor of n for some other reason, this is called the Tambara-Yamagami categorical symmetry of the group Cn. And a lot of the papers on non-invertible symmetries are exactly about this relation, which is the same one I showed you, but with a slightly different normalization. And it shows up when considering fusion rules with categories and CFTs. Okay. So non-invertible symmetries used to have different names. Other than Kramer's values duality or T-duality, they're also known as categorical symmetries. So a lot of the name non-invertible symmetry is a new name for something that has had very many different names in the past. Okay. Now let's go to higher dimensions. So how does one do that? Boson brackets to nearest neighbors, but instead of having a one-dimensional lattice, I just pick some random Boson brackets of the on all directions. So I have to pick signs now, not only on the x but on the y direction. Again, if you do the same trivial Hamiltonian, which is just sum of one array over sum over q squared, again you find a first order differential equation for q, and that means that the dispersion relation will be a single value function of k. And now the same theorem that I told you before that tells you that you have crossings of 0. Now you have crossings of 0 on any one-dimensional path from A to B that is continuous. So what you have is continuous crossings of 0. So you have, instead of 2 zero modes, you have lines of 0 modes. And in my diagram, these are these kind of 2 45-degree straight lines that meet at a crossover. So these are what people call gapless fractal modes. So you start from this idea and you don't do anything fancy, you go to higher dimensions. You end up automatically in these gapless fractal models, and you can still have some non-trivial physics.
So you're constrained dynamic. I mean, you have a dipole moment here. I mean, because of fractals.
Yeah. So if you look at what's the most interesting point for omega k, that's exactly where the two lines cross, where you get x squared plus ky squared, and then these modes here and the ones and the other crossing are conjugate to each other. So that's the usual story where you have some effective theory of dipoles.
Right.
But this is the same theory on the Brilliant zone on the lattice. Okay. I can also do the same thing to PQ matrices. So if I take PQ matrices, I still have to tell you how to split things into even and odd modes and do some story there. But you can check that you can split the degrees of freedom so that you can have Q matrices on the red dots, and then on the blue ones, you need to generate some non-trivial Poisson bracket or a non-trivial with all the nearest neighbors, so you end up with something that looks like P inverse cross P inverse cross P cross P. And if you look at the condensed matter literature, sometimes they call these correlated hopping because you have to hop on this side and this side both at the same time. I come from a different way of thinking about this. I come from QCD and stuff like that. These are like electric terms, and these are like plaquettes. So this is the same thing as some Zn kind of gauge theories of plaquettes and stuff like that. So this is kind of a nice way to think about some of these models, where you end up either on Zn gauge theories of the lattice, or you end up with this weird correlated kind of hopping, and it's a matter of training. Okay, so the most general version that we have is, okay, you want to get perverse, you have a graph. So instead of having some lattice, you just have a graph of vertices. You have coordinates at the vertices. You impose non-trivial Poisson brackets on the edges of your graph, so you have to choose signs. There's many choices. So you push all the interesting physics to the edge Poisson bracket, and this is why you've generated a bit of topology, because how things are connected starts mattering. And then if you have some non-trivial symmetry, you're allowed to twist your Poisson brackets by the symmetry, and that's how you can make whatever bosons interact with defects of your favorite theory, or with non-trivial holonomics or twisting by a non-trivial background theory. So in principle, at least, this gives rise to a huge family of models that one can study and see what happens. So to recap, now this is the end. If we start with hat bosons in one dimension, I gave you a nice argument for why they are gapless and symmetry protected if translation invariance is preserved. And then the protectedness is simple to understand in the usual sense of continuous functions, but it's also governed really by non-invertible symmetries. It really does something non-trivial in the doubling degree ring zone. In the original formulation, I didn't know that. I didn't know what non-invertible symmetries were. So, a couple of months later, I figured it out eventually, and I understood what non-invertible symmetries were. It also explains some, interesting critical theories of why they're critical at this up to a point when you have the Kramer-Snyder's duality, and it tells you some properties that you can measure just from the existence of the symmetry, which is you can predict properties of the conformal theory, which in this case is the radius of the sigma 1 conformal theory, which is one number. Once you know that number, you can basically know the operators and the theories characterized by that number. So the idea is that at least at this level, the non-invertible symmetry is controlling some number that is important or relevant for the characterization of the conformal theory. And finally, when you go to higher dimensions, it leads to interesting fractal models, and also even supersymmetric models. I didn't show you that, but there's some way to make this work with supersymmetry, because these have bosons that kind of splitting a boson in half is like splitting a fermion in half and having Majorana fermions. Majorana fermions are things that give rise to staggered fermions. So the idea was that these are called staggered bosons because of their analogy to staggered fermions, which are my so once you have both of these, they can talk to each other nicely, and you can have nice supersymmetric models. I'm going to stop there.
So just a couple of questions. No, you said that so if I fermionize a boson, alpha boson, I will get the Weyl fermion, no, in 1D. In principle, I mean the chiral boson in the continuum is a Weyl fermion.
It's two fermions, right? The simple one boson is two fermions.
Well, in the sense, in 1D, so a normal boson,
Yes.
not guard, is a Dirac, at least.
Yes.
For the central. So alpha boson is alpha Dirac, so a Weyl. If
Yes.
I split in the standard, not on my runaway. But
Yes.
so I was wondering, so maybe, I mean, is there, if I would do everything with fermionic variables, do you think that I would get something?
Yes. So this is the same story with staggering that we have.
Yeah.
We use if you use Majorana fermions on the lattice sides,
Right.
because we're in 2 dimensions. Then when you do the T-duality or the translation by 1, you get into this funny thing that you're changing the chirality of the fermions, and that there's this kind of weird relation that has to do with the staggering. That translation by 1 is not quite a translation, the staggered fermion formulation either. And that's how the Kramers-Wagner's duality for fermions shows up, which is kind of the symmetry of the Ising model and the fermion variable. But there's 2 types of there's order and disorder parameters, and you have to pass through disorder parameters. So all of that works with fermions, and this is why when you put one of these chiral bosons or one of these half bosons with fermions, you can do something where talking to each other nicely and doing the same thing more or less.
And the other things about the CFT, so you said that you have the modular invariance, also means that you have an S duality as well somewhere. Well, usually I think a modular transformation as a combination of S duality and T duality. So
yes. So when we do modular invariance, we know that these spin chains that I told you about, they're kind of the continuous limit of these statistical mechanical models that Karanov. So Karanov showed that all these models lead to these kind of things, and that explains roughly why they actually lead to modular invariant partition functions. So if you're happy with the statistical model version of these things, then that explains a little bit about why these models will be modular invariant.
okay.
But it's one of those things that the beginning point tells you nothing about that, and the final point you get something that in the continuum limit has modular invariance, and that's always very mysterious. But in this case, there's some explanation, but it's an explanation by saying, okay, this is the limit of something that has it, and should have it. I'd rather have something better. It's an explanation source, but it doesn't tell you where modular invariance really comes from. It kind of tells you that you had it hidden and you're kind of getting it. It doesn't tell you what's required in more general models to get it. Okay. Right? And this is the thing that what's the thing that you need to do to make it modular invariant? What's the deep principle that should make that happen? I don't know.
You're also stuck at a particular modular parameter here in the continuum, because the modular invariance is going to come from naturally by polyhedral.
Yes. So in some sense that's true, except that once you've been able to identify left movers and right movers carefully in the continuum limit, you can do more than that, and you can basically count the left movers and the right movers separately in the continuum limit.
And your modular parameter is naturally just purely complex. Can you get in a more general? Can you see how to get a more general modular parameter here?
No, not other than finding a way to split the left movers and the right movers in the theory, in the UV in a more systematic way, right? I need to be able to distinguish L0 and L0 bar. So if I have L0 and L0 bar, then I can twist, I can have Q to the L0 and Q to the L0 bar. At this level, I have only L0 plus L0 bar because I have the Hamilton. So part of it is to understand what L0 minus L0 bar can be. And then that's going to be tied to model elements. In principle, there's some things that can be done. I have some ideas about that. But they're kind of still baking. It's kind of, the bread hasn't risen enough.
Do you have other questions? One from, often the story is linked with higher dimensional structures and higher delusive symmetries. That's important also in this review.
Yes.
I didn't see that appearing here.
And I don't know how that shows up here either. But in the fractals,
What you relate to the defects that you put into this system?
yes. I mean, at this level, in some sense, this algebra with Q's is like the current algebra. So it's hiding some of the things that are more natural in the other variables. But it makes the symmetries a lot more manifest. So you're kind of paying a price on some things and getting something really cheap for free almost. And it sounds almost too good to be true. But the point is that, if you start from a true UV model that has lattice variables, how these projections happen dynamically about various other things, and that would lead to the separation of degrees of freedom, and that things are not trivial between neighbors. I don't know how to do that in a way that really the dynamics does that on its own.
Can you tell us a little bit more about this connection with the SUSY models?
Yes, okay. So there's something with Simon Catterall. So staggered bosons are similar to staggered fermions. So you can ask, what are the fermions that like to be supersymmetric? Those are Keller-Dirac fermions. So you can ask, are there Keller-Dirac bosons? So what's special about Keller-Dirac fermions is that you can put them on any triangulation of a manifold because the fermions are behaving like forms. And then the action of the fermions is built from the triangulation complex exact sequence. So the idea is you build the boson bracket for the bosons that follows the information of the exact sequence. So you can basically take the chain complex, have some integers, some boundary condition, or some boundary action on your favorite triangulation, and then you just make the boson brackets of the x's be C numbers over here. Okay. Now you can build a simple Hamiltonian, the same as before, but you can also build a simple supersymmetry. You can take the sum of xk, theta k, because you put the bosons and the fermions on the same places. And now you square these, q squared, there's two pieces. One where the theta k is la Majorana squared to 1, that gives you xk squared. And that's the Keller-Dirac boson Hamiltonian. And then there's the one where the theta is in different places, and because they're anti-commuting variables, you need to write commutators of the x's, and that's a C number, and that gives you this little C. And then if you stare at that, that's actually what the Keller-Dirac fermion Hamiltonian is, which is the one built from the co-chain complex building fermion. So basically, you can check that the square of this cube produces the Keller-Dirac Hamiltonian for the fermion, and therefore, any weird symmetry that one has for the boson brackets that are related to triangulations, in principle, can be uplifted to your favorite non-invertible symmetry or not. At this stage, I don't know what that is, other than Poincare duality. So it's one of those things that non-invertible symmetry seems to relate to Poincare duality. The point is that the zero modes of the fermions are the cohomology of the triangulation. And since the fermions and the bosons are paired, you know that the zero modes on the boson side are also going to be the cohomology of the triangulation, and those are the things that are going to have boson brackets equal to 0.
You said something about Poincaré duality being non-invertible symmetry.
Well, the point is
Catch
that
that.
the only thing that I know that's a non-trivial statement about triangulations is that if I take a triangulation, I go to a dual triangulation. And that changes the notion of zero forms and M forms. So there's a certain sense in which if you don't want to distinguish whether something is, let's say, a zero form or an M form, right? So things like that, you can say, okay, what would the passing to the dual lattice look like? You would go to dual triangulation, and then that would be some sort of Poincaré duality. Okay, so there will be something about Poincaré duality hiding inside.
But the Killer Dirac usually are many copies, right? So in the
Yeah, they suffer from a huge shuffling problem, but that's exactly their virtue, is that they have all this cohomology attached to them, and that's why they show up in extended supersymmetry. And the point is that there's a cheap supersymmetry that lets you add the bosons to those things. And then because you can twist the boson brackets with fluxes, I can couple free Keller-Dirac fermions and bosons to something on the boson brackets.
Yeah.
So in principle, I can couple it to some type of background gauge field. I just don't know how to do this with gauge fields. I don't know how to supersymmetrize the gauge field.
But in the case of curved background, it would be different from a Dirac because these are not fermionic variables.
Right.
All the gravitational anomaly, all the things are completely different.
Yes, and this is why I'm doing it with Simon Kachmanov system. Yeah, it's the Euler character that ends up being.
Yeah, the Euler, usually, yeah. I saw some in his paper recently about the Euler anomaly instead, and usually in condensed matter we deal with standard fermions.
Yes.
So we never get that anomaly. But,
Yeah. Yes.
Maybe we should thank David again and
Yes,
just
thank you.
release him. Oh, people online have been very quiet. I don't see.
No, there's something in the chat. Let's see what they say in the chat. No, it's just a statement that it was blurred. Okay.
And let's start the recording.
It's in more. When there's more, that's what they're putting.
What?
I'm just.
More.
See this. It's on your policy.